Okay, so this is lecture 16, and in lecture 16 we're going to talk about this kind of mysterious concept for a lot of people, which is the fact that the universe is expanding. So the title of this lecture is The Expanding Universe. So what I want to talk to you today about is how we came to understand that the universe is expanding and what the actual techniques were that went into making this measurement. The reason why we believe that the universe is expanding is not because we think it's a neat idea, but it's actually because if you go out and you look at the universe on the grandest scales and see what, for example, galaxies are doing, there is overwhelming evidence that these galaxies are streaming from us. And there is also a very tight and self-consistent theoretical understanding of why that should be happening in the context of Einstein's general theory of relativity. Now, the most important aspect of this that was discovered, oh, this is running backwards. Okay, so this is a shrinking universe. I screwed this up. The most important observation in the history of this kind of understanding this was basically a series of observations done by Edwin Hubble. What Edwin Hubble did in 1929 was demonstrate that if you look at galaxies, these galaxies have recession velocities, so they're moving away from us. And the farther the galaxies are from us, the faster they're receding from us. Okay? So I'm going to take this movie down because it's confusing us. It's shrinking. This is the shrinking universe. So just in your head, just make it go backwards, and it's actually expanding. So I'm going to give you a story. I'm going to talk to you a bit more in detail about what exactly happened. But after this series of observations that was put forth by Edwin Hubble and collaborators, eventually this gave rise to the idea that the universe itself is expanding. Okay? So what Hubble did is he measured the fact that galaxies are receding from us. That is, if you look at them, you can measure how fast they're moving away from us. And in fact, they were. What Hubble did specifically is he figured out how to measure the distances to these galaxies and showed that the farther they were away from us, the faster they were receding. Now, that general feature, if you have a bunch of stuff that's flying apart and the stuff that's the farthest away is going the fastest, that general phenomenon is what you get in a system that's expanding. In fact, if you take a hand grenade and explode it and the stuff that flies off of it, if you measure the speeds of the shrapnel that's flying off the hand grenade, the stuff that's farthest away will be going the fastest, and the stuff that's closest by will be going the slowest. So that very general relationship that galaxies that are far away are receding from us faster is qualitatively what you would expect in a system that is just grossly expanding apart. Now, this idea that this observation that the galaxies were all expanding away from us eventually gave rise to the idea that the universe itself is expanding. Now, interestingly, this idea is completely consistent with the general theory of relativity. As I'll mention later, in Einstein's gravity, the unique thing about it was it described gravitational attraction as a warpage of space-time. And a way to think about that is space itself can now be a dynamic thing. It's thought of as a dynamic something or another, right? So if you have a massive body, the reason why that acts on other things that have mass is because it actually warps the space in such a way that these other objects have no choice but to sort of change the direction of their motion, the path of the motion. So by giving us a universe, by giving us a theory that describes gravity as something that has a dynamic space or dynamic space-time, Einstein was allowing for the fact that the universe on the grand scales is not necessarily something that's fixed, but in fact could be changing in time. Interestingly enough, Einstein originally did not accept this idea. He did not embrace the idea that his theory gave rise to a universe that could be expanding. And it was only when confronted with sort of the overwhelming evidence that was mounting from galaxies that Einstein eventually accepted the idea that the universe was expanding. And this has been called Einstein's greatest blunder, and there are reports that Einstein himself claimed that this was the biggest mistake of his career for not embracing this idea earlier on, because, for example, he could have then also predicted that the universe was expanding before it was observed. Now, this idea of an expanding universe eventually then gave rise to this idea that there's a Big Bang. And I'll talk about these things in more detail in the next lecture. But the idea is pretty simple. Right now, everything's flying apart. And so then you can extrapolate that backwards in time. And if you just run the clock all the way back, you get to a point where everything was in one spot. And it's that single point where the event happened, that specific event in space-time is known as the Big Bang. Now, the thing I want to talk today about is sort of as a leading into the subject is to talk about one interesting kind of qualitative thing that this implies. This implies that you basically have a beginning point. At least in our universe, the one we inhabit, the one we observe, there is basically a point when things started. Now that's very different from an idea that time is infinite. Or maybe that all life cycle, everything is cyclical, that all time is cyclical. So one popular idea among people on Earth, and a lot of cultures on Earth have this idea, that effectively everything is part of a cycle. And historically, ideas like this have gone way back. That there's sort of a period of birth and then rebirth. And you just have this sort of never-ending cycle. And so time is sort of on an infinite loop. And it's not surprising, really, that people would have this idea. It's not a crazy idea. In fact, in the world we live in, it seems to be very much what's going on. Right? You have a cycle of seasons that repeat themselves every year. So there's cycles everywhere we look, and it looks to be on a repeating cycle. But if you embrace this idea that there was a Big Bang, which again, there's a lot of observational evidence that's pointing us to this direction, it means that this possibility of forever a cyclical circle of time, at least within our universe, doesn't seem to be what's going on. And instead, what seems to be going on is there is actually a beginning. That is, there's a starting point, and then you have time proceeding outward from there. And this is an idea, of course, that was debated philosophically probably forever, as long as there have been people to do the debating. But interestingly now, in the 20th century, and then even more confirmed in the 21st century, is the fact that that does not seem to be the case. The universe, not only do we think it had a fairly discrete beginning, but as you look back at galaxies that are farther away from us, they look different than the galaxies that are here now. In that you see development in the universe. The universe was different in the past than it is now. And so it isn't this thing that has always been one way. And it's this very idea of an infinite universe that's always been a certain way. That was basically what kept Einstein from sort of embracing this. He fell into this kind of old school idea that, space is fixed, the universe is as it is, rather than embracing this kind of more radical notion that there really was some kind of beginning. There's a story that relates to this, which is kind of interesting, so I like to talk about it in this course, called Olber's paradox. Olbers was a 19th century astronomer, and he pointed out something that's kind of interesting. So at that time, a lot of people were embracing the idea that we live in a universe that's effectively infinite, and that the universe is basically a universe of stars. Now, today we don't think we have a universe of stars. We think it's more of a universe of galaxies. But the idea, the same logic holds. Okay. So what Olber said was this. His question was, why is the night sky dark? Okay. And you might think to yourself, what are you talking about? The night sky is dark because the sun's down. But if the universe is filled with stars, okay, and if there's an infinite, and the universe is infinite, therefore there's an infinite number of stars, no matter what point you look at the sky, you should be staring at a star. Somewhere along that line of sight, you should hit a star. Okay, so if you're here in the middle, if you just have stars going forever, no matter what line you draw, you're eventually going to hit a star. And so his point was, why then is the universe dark? Is the night sky dark? Now, we can equally replace this idea. Rather than these being stars, these are now galaxies. So, does anyone have an answer? Yeah?
Something has to absorb the light.
Something has to absorb the light? That could be. That could be. So there could be something out here kind of encompassing all of these light sources that absorbs the light. That could be a possibility. Yep. Anything else? Yeah.
Not every star is bright enough for us to see it.
Okay, good. So that point was, well, you know, if once you go out far enough, the stars are not going to be as bright to us. That's basically your point. They're far enough away. Let me. Well, do you have something to say first before I address that? Yeah.
It's like we're using one single candle to light up the whole lecture room. The lecture room is not light up before the candle goes off.
Say that one more time.
It's like we're using one single candle to light up the whole room, and until the candle goes off, the lecture room is not bright enough. It's still dark. It's too small energy to light up.
Okay. So one single candle, sort of getting to this point, that if we have one single candle in this lecture hall, that's not going to be enough to light up the whole room, I think is what you're saying. And so if the candles are far enough spread apart, there's only one candle per room, we're never gonna light up the whole room. So right, so that's sort of the intuition I wanted to address, sort of this kind of intuition, but stars being too far away to be bright, it's sort of what you're getting to too. If the candles are too far away, they're not going to light up enough stuff. Now, it's actually this specific question that Olbers addressed. So it turns out that argument breaks down if you do the calculation very carefully. So one thing that you'll notice is, imagine you live here in the middle of a universe, and all of these points are supposed to be galaxies or stars or candles or something, and it goes on forever. What you said before was that, well, yeah, but if the candle's really far away, if the star is really far away, its brightness to us falls off. If you recall, the brightness of an object goes something like 1 over the distance to that object squared. Remember that? So that's the brightness that we see by eye. So if the star's really far away, they're going to get dim, and maybe that explains this darkness. The problem with that is the number of stars that should exist at a given distance also grows. Because as you go out in distance, now you're looking over a sphere that has a bigger radius. And in fact, the surface area of that sphere scales like the radius squared. And that's exactly the factor that the brightness falls off by. So although you lose because the things are farther away, you gain because you just get more of them. So for every basically tiny little wedge you look out, you will see more stars that are far away than you will see that are close. And so the fact that those stars that are far away look dimmer is entirely compensated by the fact that there's just more of them. So you actually don't win by this idea that they're dimmer because they're far away. You would need an additional effect. So maybe if the whole universe were filled with an absorbing dust of some kind, that beyond some point we couldn't see something, that would explain it. It turns out we don't see that. We don't see that effect. You don't see evidence that the whole universe is just filled with that kind of dust, although individual galaxies are. So what are some other things that could possibly explain this mystery? Any other ideas? Yeah?
Will they get redshift, like if the universe is expanding, will it get redshift to the point we can't actually see them because it's not in their visual spectrum?
Yeah, that's a good point. So you said, well, I know the universe is expanding. That's not something Olbers knew. But if we take into account the fact that the universe is expanding, then maybe the redshift of the light itself, if this light all comes out in the visible, if it's redshifted enough, if it's far away, then it spreads out and it shifts out of what we see and we can't see it anymore. It turns out that effect does matter. And it turns out that that effect is one of the reasons that helps to solve this Olbers paradox. It turns out there's actually even a simpler reason that qualitatively goes a long way towards explaining it. So let me talk about that. Let me talk about that now. So here are a few more possible solutions. So one solution is that you just say, well, your original conjecture is wrong. The universe is not infinite. So at some point you go out and then you just run out of stars or run out of galaxies and then the problem solved. The other possibility is that even if the universe is infinite, you run out of stars. So it's kind of the same answer as this one. The third one, the one that I want to talk about, is this fact that the universe has a finite age. So the fact that the universe has a finite age changes this problem entirely. And that's because light travels at a finite speed. So what this means is, if there are stars that are so far away that light cannot get to us in the age of the universe, we do not see them. And one way of thinking about this is, imagine, we were all powerful and we could just shut the light from all the stars down off. It just turns off. All light sources get turned off in the universe. You just do it. Okay? And then you turn the switch back on. We're here on Earth. What happens? Well, 8 minutes later, it's dark for 8 minutes. And then 8 minutes later, the sun starts shining. We see the sun turn on. Because that's how long it takes the light to get to us from the sun. Then we start waiting a long time. Okay? A little while later at night, we might start seeing some planets as the light has time to go reflect off those planets and then come back to us. But for a long time, for more than a year, for years, we only see the planets. We don't see any stars because the light traveling from those stars has not reached our eyes yet. But then, in about 3 years or something like that, the nearest star to us, we can see it if we happen to be looking at it in a telescope. And the nearest stars you can see by eye will light up years after that. And you can imagine fast forwarding this movie, and now suddenly the stars are turning on one by one as the light gets to us. The nearest stars get to us first, the farthest stars get to us next. 2.5 million years later, we can just begin to see the nebula that is Andromeda peek up in the sky. And then you go on from there. And you see that at this rate, eventually, you run out of time. There could be galaxies, the universe could be infinite. But beyond the point where light can travel in the history of the universe, that light has not gotten to us yet. Are there any questions about that? Yeah.
So all light is supposed to reach us eventually? Like, would dust and stuff in the way not eventually dissipate that light? Or theoretically?
Well, so the question is, will all light reach us eventually?
Like, if we just have a beam of light and you just send it straight to a point, like 10 light years away, like it'll get there eventually, even if there's dust and stuff in the way?
Well, if there's dust in the way and that light is absorbed, it will not reach us.
So light can't reach us.
Right. But if we look, for example, if we look up out of the plane of the galaxy, there's a lot of dust in the plane of the galaxy, but if we look up out of the plane of the galaxy, there's not that much dust. So then we can, in fact, detect that light. In some sense, eventually, we will detect it. Yeah?
Are we assuming that the Big Bang that we were part of is the only one that has happened, or are we just only taking that into consideration because we can't see it?
So the question was, are we assuming that the Big Bang that we were a part of is the only one that happened? And there wasn't like another one that then we can also see. I think that's what you're saying. So within the context of the current Big Bang model, which I actually haven't talked about really, there is only one per universe, and we live in a universe. Now, whether or not there are other multiverses or not, it's actually kind of, at this point, it's not an answerable question in the context of sort of scientific inquiry, at least empirically. There might be possibilities to sort of test qualitatively this idea, kind of, but right now it's kind of, we don't know. It's kind of like a conjecture. At some level, it's reasonable to think about things as this way. We live in our universe. That's the universe we can observe. And there might be other things we can't observe, but at some level, if you can't observe them, then it becomes almost like the realm of philosophy. Although I want to be a little careful because there are possible ways of exploring those ideas in our universe just kind of statistically. Yeah?
So is it right to assume that in the coming years the night sky is going to get brighter and brighter?
No. So the question is it reasonable then to expect that as we wait billions of years, will the night sky get brighter and brighter? The answer to that is probably not, and is no, sorry, and that's basically because of this point of redshift. In the long run, it's actually the fact that the universe is expanding that drives this whole night sky paradox to we don't have to worry about it anymore. And what's going on is because things are expanding away from us, that light is stretched and redshifted. And effectively what that means is the energy density of light coming at us is falling off very rapidly. So we don't expect that in the long run for the night sky to get brighter. If anything, the background light of the universe will actually go down with time. So, but if you imagine the universe that you just froze it, even the finite time thing will help explain the Olbers paradox. So, I said that what I said at the top of that last slide, and I don't think I actually said it in words, is that the universe we live in has a finite age, and that finite age is about 14 billion years. The most recent number is 13.77 billion years. So we actually think we know it to a precision that I can give you a second decimal point. 13.77 billion years. So the question is, how do we even begin to answer that question? How do people like us, okay, who've basically had, a civilization at all, for 6,000 years or something like that, depending on how you define civilization, okay? We've only existed for a species for 100,000 years, give or take. How are we in the position to answer a question like this and to give you a number of 13.77 billion years? How can we even come close to this? What are we doing to make this observation? So the answer to this begins with galaxies. Okay? That's what we kind of left off with last time, and that's how I'm dovetailing into this now. It was in trying to understand these nebulae, these spiral things up in the sky. It was in the inquiry to understand the nature of these things that eventually led us to conclude that we know the age of the universe to incredible precision. So I'm going to jump back then and start talking about this idea, this question of galaxies, by mentioning the name of James Keeler. So James Keeler was the director of Lick Observatory in the very late 1800s. Lick Observatory is on top of Mount Hamilton in the San Jose area in Northern California. It's actually affiliated with the University of California. Okay, so it is our observatory. University of California observatories have telescopes up here on Mount Hamilton. This is an historic place in the history of astronomy. This is the first place that a giant telescope was put on the top of a mountain. So this is really, Mount Hamilton is sort of the singular place in the history of ground-based astronomy because it was the first time that people actually invested money to put a big telescope up on a mountain, which gave us views of the skies that were not possible down below. So Keeler was actually using a 36-inch telescope called the Crossley telescope on Mount Hamilton. And while other people at the observatory were doing other kinds of science, he became kind of obsessed with taking photographs, the best photographs that existed at that time, of these spiral nebulae that no one knew what they were. And here's a couple pictures. These pictures were taken in 1899, these spirals. And he's got a bunch of them like this. Now, although a lot of people at this time thought that these spirals were actually solar systems in formation, they were like baby solar systems beginning to form. And the way they interpret them is like, oh, this is a star, and all of this stuff is going to wind around and become planets. And we're looking at a baby solar system just kind of not too far from the sun. But what Keeler realized is this doesn't actually make sense, because one of the things that he noticed is that as he looked deeper and deeper into these images, other galaxies started to poke out, other nebulae began to poke out. So if he would expose long enough on a single galaxy, he would see other ones behind. Sorry, he didn't know they were galaxies, but he would see other ones peek out. And he began to realize that he began to think that it's very possible that these objects were outside of the Milky Way. Now, unfortunately, he died at a very young age. He died at the age of 42. And so it's likely, well, I don't know if it's likely, but it's possible that had he lived longer, he would have been the one to really usher through this idea that these things were other Milky Ways in their own right. But the final nail in this story, so the final person who was really to solidify this idea, is Edwin Hubble. The trick was, of course, all you have is these images. So you can make up all kinds of things if you don't know how big it is, right? You just see an image in the sky. If you don't know how far away it is, you don't know how big it is. So what Edwin Hubble was able to do was he was able to actually discover stars that were variable, these Cepheid variable stars, in the M31 galaxy, in the Andromeda Nebula. And by using the luminosity period relation for Cepheid variable stars, he was able to deduce that the Andromeda galaxy was more than 1 million light years away, and therefore clearly outside of the Milky Way, and usher in this idea that there are other galaxies. This is a pretty cool image. This is an image of M31, the galaxy that Edwin Hubble was studying. This is a modern picture right here. Right here is a reproduction of the photographic plate that Edwin Hubble was using to search for these variable stars. So he would take a picture, and then he'd take a picture later, and then he'd take a picture later. And what he was looking for is this star that would get brighter and dimmer. And on this plate, this is a very famous photographic plate, because he thought what he was identifying were nebulae. But what he noticed right here is he had originally written an N, identified this spot as nebulae, but then he went back and looked at it again and realized it had gotten brighter. So he crossed it out and wrote variable, VAR exclamation point. So he knew at this point that he had done what he was trying to do. He had discovered a variable star, and he very immediately figured out that if this was true, this implied Andromeda had to be really far away. The Hubble Space Telescope, the space telescope that was named in honor of Edwin Hubble, went back about 90 years later and took an image of this star over the course of a little bit of time, several months. This is the image that Hubble made, this tiny little box. That's the field of view of Hubble. It's tiny. This is its blown up, and this little circle here is Edwin Hubble's variable star. It's obviously still there. Okay? These things live a long time. 90 years is nothing. It's still there. And this is a blown up image of over the course of time, December 17th, December 21st, December 30th, January. You see this thing getting brighter. Now the Hubble Space Telescope is able to measure these brightnesses to extreme precision, blowing away what Hubble could have done from the ground. But at some level, it was almost like in honor of Edwin Hubble that we went back and took this picture. This is, some people have argued that this is the single most important star in the history of cosmology, because it's this star that allowed Edwin Hubble to say this is another galaxy. Specifically, it's these variable stars that act like standard candles that allow us to measure distances to galaxies. So the implication is, these are these old images that Keeler was making up at Lick, up in Mount Hamilton. And here's a galaxy he was studying, but then if you look up, this is a big image that he took, but if you look in this field, this corner that looked blank, suddenly there are other galaxies revealing themselves. And so what Keeler was finding is the deeper he looked, the more and more galaxies he saw. What Hubble said was, these are actually beyond the Milky Way. So what we're looking at is a huge universe that's teeming with other Milky Ways in their own right. So the implication is, this is a modern diagram, that the universe is a universe of galaxies, and every one of these points is a galaxy like this. The next thing that people did is, now they knew what these things were, they wanted to study properties about them. And what they could also do, another thing you can do with light from these distant sources, is measure the redshift. You can measure how fast these galaxies are moving. And that was even more surprising. So eventually what that led to is the idea that the whole universe is expanding. Now, in order to measure these velocities, how do we do it? Okay, we're using the idea of redshift. And the real champion in this story, the key player in this story of actually getting the velocities, we actually have to go back in time to 1917. And there was a guy named Vesto Slipher who was working at the Lowell Observatory in Flagstaff, Arizona. Lowell actually was a guy who was fascinated with Mars. He believed that there were canals on Mars, and that this was indicative of an advanced civilization living on Mars. And so Lowell invested a lot of energy in building an observatory in Flagstaff to study Mars. Okay? But at the same time, he had great astronomers working there with him. And one of these great astronomers who was there working with him was Slipher. And Slipher was like, I'm not going to study this crazy idea of the canals on Mars. I'm going to look at these nebulae. And what he discovered is he could measure their redshifts. He noticed that he could see these absorption lines that were common locally, but they demonstrated tremendous redshifts that were so much larger than anything anyone had measured, that he was convinced that these things were not inside the Milky Way. Specifically, the redshifts were so big. So the idea is, if you recall, you have absorption lines in a spectrum associated with atoms there. And what you see is when you have an object that's receding from you, that stretches the wavelength of the light and moves those lines over a bit. And by measuring this shift, you can associate that with a velocity. And the velocities he were measuring were huge. So 2 of the first 15 galaxies that he looked at were moving at over 2 million miles an hour. It was because they were moving at these high speeds that he was in the camp of people who thought these things have to be outside the galaxy. I mean, those speeds are crazy high. And he also noticed that on average they were moving away. They weren't blue shifted, they were mostly red shifted. Yeah?
Is the Earth also moving with the Milky Way as it's moving around the sun?
Yeah, it's very complicated. So the Earth is going around the sun, and the sun is going around the Milky Way, and then the Milky Way is moving with respect to other galaxies. So if you want to really do a very precise calculation of what the recession speed of another galaxy is, you have to take into account all this other stuff. You have to kind of subtract out all of these motions. But those velocities are actually small compared to the ones we're talking about. So the speed with which the sun goes around the center of the Milky Way is like 200 kilometers per second. But once you get out to these galaxies that are reasonably far away, they're moving at speeds that are 10, 20, 100, 1,000 times that. So those corrections matter for galaxies that are nearby. Like for Andromeda, it matters a lot. But as you go to things that are farther away, it matters less and less. But we do, he was taking those kinds of things into account as best they could then. And of course, currently, we've taken them into account in a very sophisticated way. But it's complicated. So all that redshift we see. So you look at the center of the galaxy, you see a redshift. You look at other things that are nearby, you see little bitty redshifts. But the basic idea is, again, it goes back to this Doppler shift. It's the same basic idea. If something's receding from us, the wavelength stretches. If something's coming towards us, the wavelength shrinks. This is exactly the same effect that gives rise to the tendency for, you have that drop in pitch as something passes by you. Okay? So specifically what you do is you see something that looks like it has an absorption line where, say, which would be indicative of hydrogen. Say there's a couple lines that you see, or one specific line that you see, but it's not at the right redshift. It's not at the right wavelength. It's displaced to a wavelength it shouldn't be. And so the way you interpret that is, you interpret that shift, that delta in the wavelength, as a recession speed. And specifically, if you have a wavelength that is the wavelength you think it ought to be at, but it's displaced by some delta, then the thing we call the redshift is that change in the wavelength divided by what the wavelength ought to be with zero velocity. And that's proportional to the velocity over the speed of light. So if you have a high velocity, say 0.1 the speed of light, then you expect a wavelength shift of about 10%. This formula, it turns out, breaks down if the velocity gets much larger than this, and you have to use a different formula. But this is basically how it works. The higher velocity it's moving, the more you get in redshift, the more wavelength stretch you get. Yeah?
What is the 3 bars that you get?
Oh, sorry. The 3 bars, that just means this is how it's defined. So it's the same as equals, but it's like this is how we define z. Yeah?
Is this c the same constant in equals mc squared?
Yeah, this is the speed of light. Sorry. So v is, sorry. This is the velocity of the thing. C is the speed of light. Okay. Any other questions? So since we know the speed of light, you measure the wavelength, you can get the velocity. So, again, the idea is you take the spectrum of something, okay, and here are these absorption lines, and this is what it would look like if it were at rest. If it was moving towards us, all of those lines shift a little bit shortward toward the blue. You see how the double line is shifted this way? So you measure that delta wavelength shift, and that tells you the velocity that it's moving towards us. If it was moving away from us, the lines would shift the other way into the red. So you look for this specific pattern, but then you match it over here with the overall shift. And that's why it's called the red shift. It's shifted to the red. And then by measuring that change, you plug it into this equation and then solve for the velocity. Now, of course, at the time, remember, these people are just doing these observations. And so, they're not really sure exactly what to make of this. All they know is they have this spectrum of something that ought to have absorption lines that look like this, but they're all shifted out. And so they were kind of timid at first. A lot of these people were sort of timid at first about even talking about them as velocities, because the implied velocities were so large that they were just sort of nervous about it. In fact, Edwin Hubble never once said that he had discovered the expanding universe. He always said things like, I've discovered an anomalous redshift in galaxies as a function of distance. So he was, the recession speeds are apparently larger at larger distances. But he never came out and said, I discovered the expanding universe. Because it's a radical notion. So what Hubble did is he took these observed redshifts that Slipher had done, and then he combined them with his observations that gave him the distances to these same galaxies. Where he found, again, he went back to these now more distant galaxies, played the same trick he played with the variable star in Andromeda, and used that to figure out the distances. Okay, so he had standard candles by variable stars. He used that to figure out their distances. So now he had a distance and a velocity for both galaxies, for all the galaxies. And what he found, remarkably, is that the velocities of the galaxies were very well described by a very simple equation, that the farther the galaxies were away from us, the faster they were moving away. And it was directly proportional like this. This constant is now called Hubble's constant. Okay? So it has whatever units it needs to have such that when you multiply by a distance, you get a velocity out. Are there any questions about that? Yeah?
Can you repeat what you said in words about the formula?
Yeah. So what this formula is, it says this velocity v is the recession velocity of a galaxy. This d is the distance to that galaxy. h is a constant that has units, but it's a constant that you can interpret it as it's something that the universe gave us. We don't know why it has that value. And it has units such that if you take d that has units of distance and you multiply it by h, it gives you units of velocity. And I'm going to talk more about that in a second. Any other questions? OK. So this was his first plot. OK, he did this observation up at Mount Wilson on the Hooker telescope. These are the velocities that he took from Slipher. And this is the distance to the galaxy he derived with Cepheids. And he grossly observed this relationship. Now, it's not true that all of them follow right along a line, but it's a general trend. And so what Hubble did after this, so his first study in 1929, he used these Cepheids to get the distances, and he found this great relationship. The recession velocity gets larger with distance, and it hinted at the kind of thing you would get in an expanding universe. By 1931, he had gotten a lot more data and was looking at even more distant objects. And he found that the result was even stronger as he looked at galaxies that were even farther and farther away. So this is the plot from the 1931 paper with Hubble and Jameson. All of the data from the 1929 paper is down here in this little square. And so what he did is he just went out and out and out into the universe and showed that this relationship held. Okay? So along this axis is the distance. Now the unit of distance that I'm using now is megaparsecs. Okay? 1 megaparsec is about 3.3 million light years. So you're pushing about 100 million light years out here at the edge. And those things are moving 20,000 kilometers per second or so. So really fast. And there's no sign of it breaking down. Now this straight line is a relationship between speed and distance, and it's given by this formula. So the formula of a line is, y equals ax plus b. B is the intercept, okay? The intercept is 0. So the velocity is 0 if you're right on top of each other. But otherwise, this is y equals ax, where a is the slope. So the Hubble constant is basically the slope of this line. Okay? And today, a huge amount of effort has gone into measuring the slope of this line locally. And the local number is something like 70 kilometers per second per megaparsec. Now, what does this mean? Okay, it has funny units, but the reason why it has funny units is d is in distance of megaparsecs. So when you multiply it by h, you get units of kilometers per second, which is the speed you want. Does that make sense? So I'm just restating it again. This is Hubble's law. It's a relationship between v, the recession velocity, usually in kilometers per second, and d, the distance in megaparsecs. Let me give you some examples of what I'm talking about. Imagine you have some galaxies. You measure a velocity for one of them that's 71 kilometers per second. That implies that it's 1 megaparsec away. If you measured twice that, if you measured 142 kilometers per second, it would be twice as far away at 2 megaparsecs. So you could apply that to the equation. Or if you have a galaxy that's 3 megaparsecs away, you naively expect it to be traveling at a speed of 3 times 71, or 213 kilometers per second. So what it says is if you have a distance, you get a velocity. If you have a velocity, it gives you a distance. There appears to be a very tight correlation, on average, for galaxies, as if they're part of a flow that's all moving away from us. Now, as I mentioned earlier, the idea that the universe could be expanding like this is totally consistent with Einstein's formulation of gravity. That if you have a space-time that's dynamic, there's nothing that makes it fixed. And in principle, in general, even, it ought to be changing with time. So it totally allows for the fact that the universe is expanding. And in fact, not too long after Einstein published his general theory of relativity, a little while later, a scientist named Friedman was studying Einstein's equations. And he realized that, in principle, they could give rise to a universe that would generally be expanding. This is before Hubble, or actually about the same time. And actually it was a little before, sorry, it's before. He told Einstein this, and Einstein basically said, well, that's crazy. There must be something wrong with my equations. So in fact, he changed his equations. He added a term in his equations to kind of like a doorstop to kind of keep the universe static. And today we call that term the cosmological constant. It's allowed to be there based on the symmetries allowed in the equations. You're allowed to put a term in there that looks like that. Nature in principle could make such a thing happen. But it acted almost as an anti-stop to the tendency of the universe to expand and sort of held it fixed. Now later, he sort of regretted this, right? Because he eventually would realize that the universe is expanding. But this idea of a cosmological constant will creep back. And I'll talk about it next time as something that might actually be there. However, the first person to actually realize that Einstein's equations could give rise to the universe as expanding is actually a fairly unknown figure in the history of cosmology, George Lemaitre. He was Belgian. He was a Catholic priest. He was also a mathematician who was sophisticated enough to understand Einstein's gravity. He heard about the redshifts that Slipher was publishing. And in 1927, 2 years before Hubble, he actually published those redshifts and demonstrated that it was plausible that these were actually signs of a universe that was expanding, that was generally consistent with the laws of general relativity. He laid out the mathematical framework that demonstrated that. Unfortunately, he put this in a really obscure journal in Europe that no one noticed. But unlike Edwin Hubble, he actually knew what these redshifts meant. He was the first person, as far as we can understand, to interpret these redshifts in the context of an expanding universe. In fact, he told Einstein about it, and Einstein's quotation is, your calculations are correct, so he had nothing wrong with the mathematics, but your physics is abominable. So Einstein thought, like, this is just crazy. Like, there's no way that the universe is expanding like this. You know, and that says something, right? Because it's not like Einstein was sort of this in-the-box thinker who, you know, was super conservative with what he was doing. Okay? So this gives you a sense of how sort of out of the box this idea was, that the universe could possibly be expanding. He is a really interesting figure. Lemaitre is actually the first person to propose this idea of a Big Bang. He talked about this idea of a primordial atom from which everything emerged. Eventually they made up. Yeah?
Isn't it funny that he's a priest and he proposed the Big Bang?
It's very interesting, right? I mean, in fact, there are a lot of, a lot of religious people have actually contributed a lot to the history of cosmology. But it is interesting, right? You think of science and religion as at odds. But I think that is not entirely obvious that it should be, or they're even trying to accomplish the same goals. Copernicus was extremely religious. Isaac Newton was extremely religious, right? So it's not like they're anathema to each other. Let's talk a little bit about qualitatively what it means to live in an expanding universe. Because people think about this and they say, okay, well, what's expanding into what? Is it possible for the universe, as you look out, it looks like all galaxies are expanding away from us. Is that true? Are we the center of the Big Bang and everything's expanding away from us? Maybe, possibly, but it's another way of interpreting it is all space everywhere is expanding. And just because we're riding along with our expansion, it looks to us like everything's expanding away from us. So let me give you an example of that. here's my universe. Okay, I spent a long time on this. And you know, what did I do? How did I make this? Let me talk about it for a little bit, how much time I spend for you people. So I made these shapes, okay? Aren't you impressed? And then I randomly put them around, and then I captured it as one image. Okay? And then what I did is I took that whole thing, I copied it, changed the color, and then I just went and said expand by a little bit. And then I picked one of these things and I restacked the new image on top of it. Okay? So I expanded it a little bit, and I just made it expand like this. Okay? And then I did it again. Are you impressed with all the hard work that I... You're not imagining how long that took. So then I'm going to go back to the beginning. I'm going to focus. Let's pretend we live on this galaxy. And now I'm going to put the new thing that I made on top of it. But I'm going to restack it so that thing sits on top of itself. Now I'm going to do it again. Now look at what's going on. Okay? Let's look at this thing. This is the nearby galaxy to us. And imagine this takes place over 3 time periods. 1 billion years, 2 billion years, say. Now, 1 billion, 2 billion. So over 2 billion years, this thing moves a little bit. But if we go to something that started off farther away, it moves a lot more. And if I go to something way over here, it moves even more. So if you move in a given amount of time, that's a velocity. So the amount you move over the time you move is exactly the velocity. So given that this thing moved less, it's moving slower, and this one's moving more. The farther it is away from us, the faster it's moving. That's exactly what's observed. Okay? Now everything's moving away from us. Now let's pretend we're an alien civilization and we live on a different galaxy. What do they see? They're riding along on this galaxy. So I'm going to restack everything on top of this. And do it again. So from their perspective, they see the same thing. They see everybody moving away from us. And in fact, this is us. So they think we're receding from them. We think the other way around. And again, the things that are farther away are moving the fastest in the same amount of time. Does that make sense? Okay. Now I know we have skeptics in the audience, so we're going to do it one more time. See, doesn't matter what you do, you always get the same. That's how we interpret what we see. So in a sort of we want to think about the Copernican idea that there's nothing special about us. We're not at the center of the universe, and there's an easy way to interpret it. If you interpret it this way, it doesn't demand that we're special. In fact, everybody should see what we're seeing at some level. Does that make sense? So are there any other questions about the expanding universe in that context? Okay. So let me now talk a little bit more about time. So apparently we live in a universe that's expanding. All of the galaxies are headed away from us. If you take this thing to its logical conclusion, that everything's headed away from us now, so if we backed up in time, everything was closer and closer and closer. You know, you can interpret an image like this as being, this is where things are now, this is where they were in the past, and you could keep shrinking it down and down and down. So what that means is at some point it was smaller, and you'd like to figure out, when was that point? How long did it take for the universe to go to basically 0 size? And that's what gives you your age. Okay, so early time, later time, late time. And the question of how old is the universe, at some level, is just related to how long ago was it that the size was 0? And that's the beginning. Now, this is going to be the topic of sort of the first part of the lecture next time. But let me kind of give you an introduction to this general idea. Okay? What we observe now is galaxies moving at some speed. okay? And we want to know when it all started. You can do this calculation pretty easily, right? If you see, let's say your friend lives a mile away. And they're supposed to meet you at your house at 8 o'clock at night. And they roll in at 8:30. You know they left late, right? The way you know they left late is you look out your door and you see them drive 60 miles an hour right up to your house and stop. So how long did it take them? They live a mile away. They go 60 miles an hour. How long does it take? A minute, right? Am I right? So, right? So you're like, look, I know you left your house about, 1 minute ago. So don't give me that about, you're sorry you're late. Okay? So you can estimate how long things have taken if you measure a speed now. Now, what's your friend going to say? What's your friend going to say, especially if they drove down the 405 to get to your house? Yeah, I wasn't going 60 miles an hour the whole time. Come on, I just sped up. I was just speeding up. I was going slow. It was took 2 hours. Right? So if we want to do this calculation, that's a reasonable guess. A reasonable guess is you take your current speed and you back up to how long it took to get there. But you don't know for sure because they could have been speeding up or they could have been slowing down. The problem we're trying to solve is very similar to that, but it's a little bit more complicated. So it would be analogous to this. The universe is expanding, okay? So as the universe expands, it is feeling gravity from all those other things in the universe. So it's much like, imagine you throw a ball up in the air. You start off with some speed, but the speed of the ball is going to slow down as it's on its way up. So what we're envisioning is lots of balls thrown up from the surface, and they're all kind of going out, okay? The calculation we're trying to do is we're up on some ladder, okay? And we know we're a mile off the ground. A ball comes by us, we measure with our stopwatch as it goes by, it's going 60 miles an hour. Now roughly you would say, oh well, it left the ground about a minute ago. It's going 60 miles an hour, it's gone a mile, it's gone 1 mile, that's about a minute. But is that right exactly? No. Is it going faster now or slower than it was when it left the ground? Slower, because gravity's pulling on it. So does that mean it got here quicker than a minute or slower than a minute? If it took off going faster than it is now? Who thinks it's quicker than a minute? Okay, who thinks it's slower than a minute? Okay, that's not enough thinking. I want everybody to vote, okay? Listen to me. Okay, listen, I know you're not paying attention anymore, but you gotta listen to me. Do your best, okay? You've got a ball. It's going 60 miles an hour. It's been thrown up, and it's right now going 60 miles an hour. If it's been launched off the surface of the Earth, is it going faster or slower now? Slower, because it's being slowed down by gravity, okay? So if it was going faster before than it is going right now, and you would think it would take a minute if it was going its current speed, but in fact, on average, it's been going faster than that. Would it have taken less than a minute or more than a minute? Less than a minute. Okay, good. Okay. So if we imagine that launching point as the beginning, okay? If we imagine that launching point as the beginning, that's the Big Bang. So we can roughly estimate the age of the universe by measuring how fast galaxies are moving now. But that only gives us like an order of magnitude number. If we want to know precisely or have a better guess of the age of the universe, we want to know how fast it was going earlier, then later, then later, then later. And that's linked to, in this experiment, the mass of the Earth. The more mass of the Earth, the more it's been slowed down and the faster it was launched at the beginning. So the more mass of the Earth, the shorter the amount of time it's taken to get here, because it's been slowing down more to get to 60. The less mass of the Earth, if there's no mass on the Earth, it's just been going 60 the whole time. So then it does take your minute, you get your minute again. So in order to, the analogy is similar. In order for us to measure the age of the universe, we have to know how much what the density of the universe is, how much stuff is in it. Because if we know how much stuff, then we can work out how much it's been slowing down. Yeah?
Then how does momentum come into play? Because if it's more massive, then it would have a greater momentum, right?
Well, so the question was, how much does momentum matter? So it turns out the deceleration of objects, okay, on Earth is independent of the mass. Okay? So the force due to gravity on something is proportional to its mass. But so the force equals mass times acceleration. So those masses cancel out. So all objects, no matter what their mass are decelerated at the same rate. So it doesn't matter what the mass of the ball is. So it doesn't matter if I'm throwing up ping pong balls or tennis balls or bowling balls. I can do exactly the same calculation. Okay. All right. So I'm going to talk about that general concept next time. Weighing the universe, measuring the age of the universe, and then the surprising outcome of that experiment, which is something called dark energy. Okay. Talk to you next time.